Okay. Okay. Is it going to work this time? Yes, it is going to work this time. Nice. Okay, so this will be a live stream where I answer stuff about this math test. It's a pure math test on real and complex analysis. Says it right there. Hi Felix. It didn't work the first time. I ended up streaming on a different channel. Okay, so let's look at the first question. It says, prove by verifying the Epsilon-Delta definition that the limit as x approaches 2 of x cubed minus 3x squared plus 6 equals 2. Okay, so let's go ahead, answer this. Hey, calculus videos. Nice to see you here. So, let's go ahead and get the limit in here. Oh, the 80 Mazes is here. He was on my stream when I messed up. I accidentally streamed on my meme channel. So, so the question is, the limit as x approaches 2 of x cubed, ew, let epsilon be less than 0, you absolute monster. X cubed minus 3x squared plus 6. So minus 3x squared plus 6. And this is equal to 2. Well, let's go ahead and write out the Epsilon-Delta definition. So we have, for all epsilon bigger than 0, there exists delta bigger than 0, such that the distance between x cubed minus 3x squared plus 6 and 2 is going to be less than epsilon when the difference between the absolute value between x and 2 is less than delta. So let's go ahead and analyze this. Okay, so right there, that's just going to be x cubed minus 3x squared plus 4. And I want this to be less than epsilon. Now that's a thing. Can I factor like x cubed minus 3x squared or something? So how exactly would I get epsilon here, a value for epsilon, given x minus 2? Well, can I factor out an x minus 2 here, is the question. Well, let's just do some algebraic division. X squared plus 4. X minus 2, that's going to be x squared. X cubed minus 2x squared. Subtract it. I get there minus x squared plus 4. That's going to be minus x. I actually get a plus 2 something there. I know this is trivial. Okay. I'm just confused on how to get the specific things here. I'm probably very dumb when it comes to this. So how can I, maybe I could just do when x minus 2 is equal to delta, so that x equals 2 plus delta, maybe something like that, and then plugging it in there, and then solving for delta or something. I don't know. Okay. This is not going well so far. So, chat, give me an idea. Just give me an idea how to get delta here. You know what? Let's just That's probably really easy. Okay. Let's go ahead and start with the delta and then get the epsilon. So x minus 2 is less than delta, so that x minus 2 squared, x squared, minus 4x plus 2 is going to be less than delta. And then multiply that by x, so x cubed minus 4x squared and plus 2x. It's going to be less than delta. Let's add these two together. So I get 2x cubed minus 4x squared, and then plus 2x plus 2. We're close to getting to x cubed minus 3x squared plus 4. Oh, Brennan. So, let's maybe, okay, how could I get x cubed is the question. Let's cube it then. So x cubed minus, okay, so x squared, that's going to be 4x cubed. So x squared with x squared is x to the 4th. Okay, that's not going to help us. No, wait, no. X cubed minus 4x squared, and then minus 2x squared, so that's 6x squared, and then plus 8x, and then plus 8x, and also x, and also 2x, so that's 10x there, and then minus 4. It's also going to be, it's going to be less than delta cubed. Hey, derived mathematics, I'm just struggling to do a basic problem. Okay, so I have to prove that the limit of this is equal to 2, and it's not going very well. So I start off with x minus 2 is less than delta, and then from there I squared and cubed it, but it's not working very well. Epsilon-Delta limits, yes, and I'm not doing well at it. So you can tell my supreme intellect. Okay. What should I make delta equal to? So maybe I should do like delta equals the inverse function or something. Okay, so what I want to get is x cubed minus 3x squared plus 4, and I want to get from there to delta. Okay, so let's look at this. X cubed minus 3x squared plus 4 less than epsilon. Now the thing about this is that it isn't like a quadratic or anything, so it's not as easy to solve. Okay, shut up. Look, okay. Okay, how do I factor this? I forgot how to factor stuff. This is really showing. Okay, so right there we're going to have 1, 2, and 4. So can 1, 2, or 4 go into this? Well, is 1 a root? 1 is 1 minus 3. No. So that's 8 minus 12 minus 4. 2 is. So, wait. okay, so x minus 2 has to go into this, which I just said it wouldn't go into. So that's 8 minus, yeah. So x minus 2 has to go into x cubed minus 3x squared plus 4. Okay, that's going to be x squared, so x cubed minus 2x squared. Subtract that, that's minus x squared plus 4, so that's going to be minus x. Just go ahead and do that. That's minus x squared plus 2x, getting us, we're going to have just 2x left, and then plus 4, and that's 2, so plus 2. So it's x squared minus x plus 2, which, you can't factor further. So that doesn't help. It's black pen, red pen, isn't it? Okay, so this doesn't seem to help factoring it out, but an x minus 2 is factored out. So that can help because the x minus 2 is there. X minus 2, and x squared minus x plus 2. Okay, so we're getting somewhere. Basically meaning, I'm like so close to being... So, I'm so close to just getting it again. So, 1 minus 1. Okay, now 2, 4 minus 2 plus 2. No, okay, so you can't factor it any further, and that's very close. So right here, what can I prove about this? That looks very similar to x squared minus 4x plus 4. It's sort of like that, except these two, this is a 2, so it's sort of close to this as well. So if I made this a plus 1 there, then that's going to be less than delta squared plus 1. Then I can't... So, plus 1, no, it's plus 2. So, x squared minus x plus 1, yeah. So, it's really close to being that, which is just delta squared. Except I have to add a 1 to it, so let me just write it like that, yeah. So this is going to be x minus 2 times x minus 2 squared plus 1. Like that. It's going to be less than epsilon. Distribute that. That's going to be x minus... Oh, no, x minus 1 squared. Yeah, it's x minus 1 squared, so... That doesn't work as well. Okay, so what if I do x minus... Okay, so guys, stop. I started 13 minutes. Yes, I can't get past this problem. You know what? Skipping it. I have no clue who the 80 Mazes is. No clue who you are. Get out of my stream. Okay, so I guess you do something like that, something along those lines. So what if I do x minus 2 squared? What do I have to add? Well, I'm going to have to get plus 3x and plus 6. Okay. You know what? Just... I failed this test. That's what we got out of this. Okay. If just do this. Okay, I'm gonna leave that up there. Do it yourself. Wait a minute. Wait a minute. So we got x minus 2, multiply that by x squared, minus x plus 2. This right here is definitely going to be less than, well, I needed to be greater thans, so that I can have like a series going that way. So this is going to be greater than x minus 2 times, and then I want it to be something smaller in here. So I could do minus 2x plus 2. That's definitely, it's going to be greater than that. This is assuming x is bigger than 0, which is fine. So now x minus 2x and then plus 1. I could do that, because that's definitely going to be less than, and then that right there is just x minus 1 squared. Very close. So this is x minus 2 times x minus 1 squared. Now the thing is that I can't use x minus 1 squared. Okay, so how about I do x squared minus 4x plus 4, just so that I could get that sweet sustenance. So right there, I'd have to have it that minus 4x plus 4 is less than minus x plus 2, which is multiplying it by 4, so that's false. No, it's not. It's not. Which would imply that minus 4x is less than minus x minus 2, so that 4x is bigger than x plus 2. X is bigger than 2/3. If I assume that, then I can assume this, which would then be equal to x minus 2 cubed, which is then going to be actually, I want it to be less. I want it to be the opposite, don't I? I want it to be less than, so that right here I could get a less than and then have, yeah. So I needed this to be bigger than. So I have to have it less than 2/3, which doesn't make any sense. Read my hints. Choose delta less than 1. You have a bound on x squared and 2x. So if I choose delta less than 1, then the x minus 2 is less than 1, so that x is less than 3, x squared is less than 9, and 2x is less than 6. And then I could just plug in. I'm stupid. I'm very, very dumb. Okay. Which is going to be less than. So then I'd have x minus 2 times 9. Oh, 4. I need. Okay. Right there. X minus 2. Multiply that by 9 minus x, which is minus x, which is 3. And then plus 2, so that's just 8. 8x minus 16, which is definitely going to be less than. That's just because it's 8 times that. 8, so it's going to be less than epsilon. Implies that x minus 2 is less than epsilon over 8. And this is for delta less than 1. And this is for x less than 3. If I assume x is less than 3, then we have it. Okay, yeah. It has to be the absolute value, but, when, okay. So let's take the absolute value of that. Let's also assume x is bigger than 0. So basically, the bound would be epsilon over 8 if x is less than 3, and if x is bigger than... If the x is not less than 3, then we won't have those bounds. So I see how we can do it. Let's just move on. That took way too long. This is basic analysis, yes, but I'm bad at it because I'm not very smart. Okay, let's scene 2. Okay. You won't get the next one. Now, I'm actually good at not that sort of stuff. Okay, assume that f and g are real-valued functions defined on a deleted neighborhood of A, an element of R. Further assume that limit as x approaches A of f of x equals L, and that the limit there. Okay, so let's prove it. So what, let's do limit as x approaches A, f of x, g of x. So we go ahead and look at the absolute value of f of x, g of x, and then minus a, right? And we say that this right here is less than epsilon for x minus L times m. So L m is less than epsilon for x minus a less than delta, and I'm assuming all the different things. Okay, so what do I know? I know that f of x minus Lm, or minus L, is going to be less than epsilon for that same condition. So I could make it less than any sort of condition like that. So how about I make it less than the square root of epsilon? That could help. And then the absolute value of g of x minus L, I can also make less than the square root of that, and then I can multiply these together to get f of x, g of x, minus m. This one is m. And then we're going to get an extra term, which is going to be g of x times L, so g of x L minus f of x m, and then plus Lm. That's not... Okay. That's far off from what we want, but I guess it's somewhere. So now I could probably split this up into the absolute value of f of x, g of x, and then the absolute value of g of x L, and then the absolute value of f of x m, and then the absolute value of L m. And then I have to deal with those, which isn't good. Felix. Okay, so maybe there's an even better way to do this. I feel like there is. This was a bad idea. So, right, because the absolute value of... Yeah, less than. Okay, so I feel like I have an idea. Okay, so Okay, so I could choose any, like, form of the epsilon just as long as it's like that, still bigger than 0. So complex analysis. Okay. I want to do this. I know it makes me look very stupid, but I feel like I'm close, though. Okay, so I feel like that's putting me on the wrong track there. Maybe I could look at, like, a special case. Oh no. Oh no. Okay, guys. I feel like I want to continue on this idea, and there has to be like an expression for this. Right? Ooh. Okay, so none of my markers are working now. Ugh. Okay, so maybe the pink one. Okay. So now hint. Wait, they gave me a hint that I just ignored because I'm okay. So we can assume that it's less than the absolute value of h plus 1 in some deleted neighborhood. So okay, how could we use that to our advantage? So I guess I could also use the fact that absolute value of f of x is going to be less than the absolute value of L plus 1. Absolute value of g of x is going to be less than the absolute value of m plus 1. Who knows? Who even knows? Okay. So, yeah, there has to be like an expression for this. Right? So maybe I could do like, okay, here's something I could do. I'm going to ignore that hint. That might not be good. So I could do like f of x minus L, and then multiply that by g of x minus m. It's basically what we were doing before, except I have to add in my error terms. And what are my error terms? It's what are my error terms? That's f of x squared. Okay, so it's my error terms from before, which were like what m or okay. It's plus f of x m and then plus g of x L, because there are minuses there. I get the pluses here. That should be it. Okay, so is there something else I could do? Would that give me it? No, because I'd have... Like, are you... Okay, there. How far into it did I have it muted? How far into it did I have it muted? Do you understand what I did there? So I think what I did was I like split that up into a bunch of different times. So okay, my reasoning was I wanted these two, and so I just added the error terms and I subtracted two LMs so that this plus LM would become a minus LM, because those minus LMs there, and then that ended up like factoring like that, and that was pretty good. So yeah, that should work. Cool. Yeah, look at that, I actually did one of them. Okay, using limit laws, evaluate that mess, that absolute mess. Oh no. Oh god, no. I think I'm gonna skip that one. That would be boring. That's just boring, I think. Yeah, so I'm gonna skip that one. I did something, guys. Okay, so verifying the definition that g of x equals x squared over 1 plus x is differentiable on r removing minus 1. Okay, so all we have to do is show that the limit, as I'm going to use the h definition, even though sometimes that's a little harder, of x plus h squared on 1 plus x plus h minus x squared on 1 plus x all over h. Oh boy, haha. You know what? Let's do the other definition. Oh boy. T approaches x. On the top, we're going to have t squared. On the bottom, we're going to have 1 plus t. And there, we divide it by t minus x. We're cool. We got this. Okay, this is going to be equal to the limit t approaches x of t squared 1 plus x minus x squared 1 plus t over 1 plus t times 1 plus x, and that's times t minus x as well, so that this is the limit t approaches x of t squared plus x t squared minus x squared minus tx squared all over 1 plus t. Okay, I'm going to multiply that through. So that's going to be 1 plus 2tx. No, not, yeah. Yeah, 2tx plus, no. So 1 xt and then xt plus x plus t plus xt. And then that multiplied by t minus x. Now that top looks like it could be factored, although I have no clue how. Actually, I do have a clue how. It's grouping. Right there, factor out of t squared, that's 1 plus x. Right there is not 1 plus x, no. Everyone here wants the complex part. Everyone wants the complex part. Let's go to the complex part then, guys. You want me to skip Riemann integrals? You sure about that? Okay, this is complex, right? This is, yeah, this is B. That's A, this is B, so this is complex. I just realized I'm not showing the right things. Okay, so just hold on that. There. Okay, you guys are fine with real analysis? Okay. So I'm going to skip the ones that I think are boring. But this one, I kind of want to do. So this one, it just seems like it could be factored, but it looks like one of those standard factoring things. T squared plus xt squared minus t x squared t plus minus x squared. Right? Maybe here, maybe I switch these two. So minus x squared t and plus xt squared and over blah, 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 equals the limit t goes to x of, right there it's going to be 1 minus x t minus x squared. And right there is going to be t squared minus x. Dang it! Are you joking me? Okay, so, sorry, I keep forgetting to switch. I just hate derivatives. So, maybe we could do something here. So, H definition is trivial, man. It's basically trivial, man. H definition. What's H definition? Okay, so this is just okay, so I don't think I can factor it. That seems like it's off the table now. So how on earth can I evaluate this now? Oh, the pic is pretty blurry. Let me Oh, the H definition is trivial. Okay, I'm sorry. Yeah, it's probably easier, and I'm just... Yeah, it's because of the marker I'm using. Hopefully my purple marker's better now. Yeah, okay. Let me get a new marker, guys. Blue. Get a blue marker! Hey! Okay, guys. I'd be very bad at this test, but you get 3 hours. You get 3 hours. Okay, so limit x. That is so much better. I should use this marker more often. Okay, the limit as h goes to 0 of x plus h squared, which is x squared. I could leave it as x plus h squared for now. X plus h squared over x1 plus x plus h minus x squared over 1 plus x over h. Okay. Limit h goes to 0. Okay, that right there, I could... Yeah, I'd have to multiply the top and the bottom by 1 plus x for this one. So x plus h squared. I'm going to write that out. X squared plus 2xh plus h squared. Multiply that by 1 plus x, and then minus x squared times 1 plus x plus h. And then this is going to be on 1 plus x times 1 plus x plus h times h. This is going to be equal to limit h goes to 0 of, okay, that's going to be x squared, or let's do x cubed, plus, that's going to be 2h plus 1 times x squared, and then plus, that's going to be x next, so 2xh, and then h squared, so 2h plus h squared times x, and then plus h squared should be it, and then x squared minus x cubed plus x squared minus x squared h. Okay. Okay, so, and then this is going to be over 1 plus x times 1 plus x plus h times h equal to, am I doing something wrong? The limit as h goes to 0 of, I'm going to have x cubed, and then plus 2hx, oh no, x cubed goes away. I'm left with 2hx squared plus, okay, I have x squared h there as well, so that becomes an hx squared. And then the x term, there's no x term here, so that's going to stay the same. 2h plus h squared x, and then plus h squared. That's it, okay? And then factor out all the h's, so that this becomes this. Then this is going to be on 1 plus x times 1 plus x plus h. These seem like very similar things. So I could probably factor the top, right? Is that what I'm... No, you can't factor something like that. Okay, so... Oh, this is x squared. No, x squared isn't there. X squared gets canceled out, so there's no x squared. It's just this. Okay. No, it's 8hx squared, yeah. hx squared. And then I factored out the 8. Okay, so I was right. Okay, so... Okay. Oh, man. That's gotta be it. So where can I go from here? I guess I'd have to multiply the top and the bottom and then split it up. So let's split this up into a bunch of different ones. So this is going to be x squared. I can plug in for h. Is that? Yeah, I can plug in for h now, which is going to be equal to x squared plus 2x. And that's going to be over 1 plus x squared is 1 plus 2x plus x squared. And this is going to be 4x not equal to 1. Okay, that's how you do that. Sorry, I'm not very smart. Okay, so let's do number 2. That was... Okay, state carefully Rolle's theorem. Rolle's theorem is the... So for f, a function from a to b into R, such that... Hopefully my mic didn't cancel out. Okay, it didn't. Okay, so then such that f of a equals f of b, and is it that f is differentiable? It's continuous. And f continuous, there exists C, an element of AB, such that f is differentiable at... No, it's not continuous. It's differentiable. It has to be differentiable. And differentiable on AB. Okay. Thank you. Differentiable on AB, then there exists a C, an element of AB, such that f prime of C is equal to 0. That's the theorem. The mean value theorem is that for f from a to b into r such that f is differentiable on AB, there exists C, an element of AB, such that f prime of C is equal to f of B minus f of A over B minus A. Okay, and then deduce the mean value theorem from Rolle's theorem. Number 3 is Maclaurin series and triangle inequality. Yeah. Okay, then from there I have to deduce. Well, then let's just... Okay, so what I want is a function g, a new one, such that g of A is equal to g of B, and that g prime of C equals 0 is equivalent to saying that f prime of C is equal to f of B minus f of A over B minus A. So let's just solve for 0 here. Just get 0 on one side. So B minus A, f prime of C, and then I'd have to add f of A, subtract f of B, set that equal to 0. And that's g prime of C, so let's just integrate it, I guess. So B minus A times f of C, and then plus f of A minus f of B times x, or I'm gonna replace it with x. So let's make this a function, right? So is g of A equal to g of B? Well, g of A is going to be f of A there times B. Okay, so let's write. Okay, it's going to be B f of A minus A f of A, and then plus f of A times A minus f of B times A. Oh, the f of A's there cancel out, and then I'm left with that. And then the other one would be B f of B minus A f of B plus f of A times B, then minus f of B times B. And then these two cancel out, and we're left with the same thing, so that condition is checked and that condition is checked, and then we just use Rolle's theorem on that. No, guys, natural log of 1 plus x there? No, you can't use Maclaurin series because Maclaurin series has a radius of convergence. So this is for general x bigger than 0. You can't just use, no, this is not Calc 1. So you can't just use the Maclaurin series there. You definitely can't, because Maclaurin series has radius of convergence, and we want it for general. So my thought here, easy way to do it, it's not Taylor series. No, don't do Taylor series. That's very bad, because Taylor series for the natural log has small radius of convergence. It's really hard to work with it. So I'd imagine that usually with things like this in like topology, if you look at like proofs of Brouwer's fixed point theorem or whatever that's called, you look at like natural log of 1 plus x, and then I subtract off of it x, which is the thing I want, and then I subtract off of what I want, and then plus x squared over 2 minus x cubed over 3. I don't think you could do Taylor. So maybe I could look at this and then prove some facts about it by doing a derivative. So let's, because if I do like I could maybe do something like the derivative is like less than a certain point here or something like that. I don't know. You could use the exponential function on both sides. True. I'm not sure that'll help though. I think polynomial with the exponential isn't very good. So let's take a derivative. This is 1 over 1 plus x. I hope it is, unless I'm very dumb. Minus 1 plus x, and minus x squared. Yeah. That looks pretty simple. Can I... but there's a minus x squared. Oh yeah, that could help. Yeah, actually. So if x is bigger than 0, what can I prove about this? Well, what's this going to be equal to, first of all? That's going to be minus 1 minus x, then plus x plus 1 plus x squared, and then minus 1, then minus x squared minus x cubed. So it's just 1 minus x cubed on the top. Minus 1 minus x cubed on the top. Minus 1 minus x cubed over 1 plus x. Or 1 plus x cubed over 1 plus x, and I negative out front. Ah! So if x is bigger than 0, then this is bigger than 0. It's going to be bigger than 0, so that its negative is going to be less than 0. And then if x is less than 0, then this right here, by the same exact reasoning, is bigger than 0, right? Is that right? So my idea is that we show that it has like a curve like that. So basically what I did here was show that when it's less than 0, it's increasing, and then when it's greater than 0, it's decreasing. Right? Yeah, that's what I just showed. So I'll call this f of x. So f is increasing on, where's it defined? It's defined from minus 1 to 0, and decreasing on the interval from 0 to infinity. So natural log of 1 plus x minus x plus x squared over 2 minus x cubed over 3, that right there is going to be less than f of 0, because it's decreasing. Because it's decreasing, it's less than f of 0. With f of 0 is 0, 0, 0, so that it's less than 0. So that natural log of 1 plus x is less than x minus x squared over 2 plus x cubed over 3. Does that not work? That seems like it works. Yeah. How does this not work? Because it's decreasing past 0, so that has to be less than that, which is 0. And this fact is true. Right? Okay. I think I've seen a similar proof. That's how I got the idea. I've seen like a proof that like natural log of x is bigger than x, or there's just a bunch of stuff where you look at the difference. Yeah. the proof for natural log of 1 plus x and x being, we don't care about x less than 0, yeah. State the epsilon-delta definition. Okay, so this is basically just a simpler version of what we were doing before, just easier. That's what this next section is. Let me show you guys it in full screen. So, state the epsilon-delta definition. So let's state the epsilon-delta definition. Okay, so we have it that the limit as x approaches a of f of x is equal to a for f from some u removing a into r is true if for every epsilon bigger than 0 there exists a delta bigger than 0 such that for any x an element of u removing a, the difference between x and, I can't say it's equal to, I'm going to say it's equal to L, such that the difference between x and a is less than delta, implies that the difference between f of x and L is less than epsilon. That's the epsilon-delta definition. Everyone has it memorized. We're doing it on a deleted neighborhood. Look at it. So we don't include a. We can't include a, so you can't do f of a. Wait, am I stupid? I can't believe myself. Okay, this is just from an open interval of u into r, and then of course f of a there, and we don't include that. F is continuous at a if. There. Sorry, I'm not the smartest. Okay, so assume G is that. I was looking at the next question. That's what I was. Okay. I have done uniform continuity. That's okay. So we're proving that the composition of things is whatever. Okay, so what do I know? So I have F and G. So let's write out the definition here. So for all epsilon bigger than 0, there exists delta bigger than 0, such that, well, let's go ahead and do it on F first, such that the difference between x and a is less than delta, implies that the difference between f of x and L, did they call it L? They usually call it L. They haven't defined. Oh, f is continuous. So f is continuous. Right here I could just do f of a. Or is it on a deleted neighborhood? On a neighborhood of L. So I'm doing the limit as x approaches a. Oh, I could do this on a neighborhood of L. So I could do this for L. So L there, f of L here. That wouldn't help. A here, f of a here, less than epsilon. And then I could just take x equals... Okay, so maybe... What's a deleted neighborhood is where you do an open neighborhood around a point, and then you remove that point. That's what I'm guessing. I've never heard that before. So I also know that for here, I also know that the difference between g of x and L is less than epsilon. So maybe I'm going to put... Wait. Actually, just realized something. I could do L here. I could do f of L here. And then I also know that g of x minus L is less than epsilon on this same exact thing. For the same exact statement. So what I could do... Okay, so let me write out this other thing. So for all epsilon prime bigger than 0, there exists delta prime bigger than 0, such that I could do g of x removing a less than delta prime implies that g of x minus L is less than epsilon prime. What I could probably do, is I'm going to replace this with a u or y. I'll do y. Okay, so, and then what I could do is then here I'll replace this. Okay. And then this, I could probably translate, right? I could translate this to here. Let's take epsilon prime equals delta. Delta here. So this is delta here. I'm going to take epsilon prime equals delta. So absolute value of g of x minus L is going to be less than epsilon. It's going to be less than delta, which implies that from this one, I can then do f of g of x removing f of L. It's going to be less than epsilon. So basically meaning, for every epsilon bigger than 0, there exists a delta prime bigger than 0, such that this implies that. Cool, that works. Number 3, it's just calculating Taylor series. This is not a calc exam. This is a real analysis. Real analysis is surprisingly very different from calculus. Guys, do you want to see the next section? Assume f is a bounded function on the interval a to b. Define a partition, define the upper integral and the lower integral. And then here, look at this. Okay. Guys, this is not a low-level calc. Did you guys learn about the formal definition of the Riemann integral in early level calc? No, you didn't. Because this is real analysis, guys. Thank you very much. I have a video on that thing right there. And it goes into complex analysis after this, guys. Look, let me scroll down to the next section. Look at this. It's like log of z, principal logs. Right here we have contour integrals. Right here we have stuff about residues. I think there's something about suppose that f is holomorphic on the analyst d equals z. Look, guess what? Stop. It's not early level calc. Thank you very much. Lebesgue integrals in early level calc? Okay, so let's do this Riemann integral. Yeah, this is an early level calc, guys. Okay, so let's go ahead and do the first problem. Define what a partition of AB. So a partition is a set P equals a set x1 to xn such that A is equal to x1 is less than x2 is less than xn equals b. And so sometimes you'll see less than or equal to. I don't know the thing in whatever notation they're using. Predicate logic, I've studied a little bit of it. Define the upper integral. So now let's define the Riemann integral. So let m equals the sup of f. Let mi equals the supremum. No, it's the supremum. I'm right. Big M equals the supremum of f of x for xi minus 1 less than x less than xi, or less than or equal to. We do that, and we do lowercase mi equals the infimum of f of x for xi minus 1 less than or equal to x less than or equal to xi. Then, after that, we say that delta xi is equal to xi minus 1. So then after that, we do, I'll say that the upper integral along a partition f is equal to the sum from I equals 1 to n of I equals 2 to n, right? Of delta xi times mi. And that the lower partition f is the sum from I equals 2 to n delta xi times lower mi. Yeah, that looks about right. And then we say that the integral from a to b of f dx upper is equal to the infimum of u of pf for partition p, and that the integral ab lower f dx is equal to the supremum of lower pf for partition p. Prove the product rule from first principles. I have a video on that, actually. I have a video on that. Okay, prove that the lower and upper bounds satisfy. Show that for any partitions for any partitions? Okay. Let's prove that. Okay, I still have room on my board. So, suppose Q, P are partitions. Okay, so we know that for subsets, this exam is kind of disappointing. Yeah, like a lot of it is just brute calculation that you have to be good at. suppose QP are partitions. Let's, the lower part of QF is going to be less than the lower part of Q union PF, right? It's going to be less than or equal to that, which is going to be less than or equal to the upper part for Q union PF. And then from there, all I have to prove is that the upper parts work out. So the upper part for Q union PF, and I have to move this down. So I have to move this down to the upper part of PF. So, how on earth? Haha, sorry for disrupting. Please continue. I'll be quiet. Have you started research on anything from what I've seen from your channel? You would enjoy it. I've done like a bunch. I've really not done my own research, really. But, so, my problem right now is this. Okay, so, maybe that Q union P wasn't the best idea? Okay, so the upper oh, I have this backwards. Sorry. So if this is a smaller thing, I could do that. Q intersect P. So Q intersect P. Oh. Easy. Just look at the Taylor series. Okay, yeah, so I had that one wrong. So that would be less than or equal to the upper Q intersect PF, which is then less than PF, like that. Then we proved it. Okay, that was easy. That was pretty easy. Deduce that. Okay, yeah. The lower integral dx is equal to the lower one, the supremum of these L's, PF for partition P, okay. Now I proved that for any partition P that I can show that it's bigger than. So that this has to be less than or equal to the infimum of the union of PF for partition P, which is the upper. Since for any x an element of the sup1, there exists a y an element of the inf1 such that x is less than y by the last one. Like that. Okay. Okay, so we have this function, and this is just calculating. That's just calculation. I don't want to do that one. So, let's move on. So, let Z be an element of that. Determine the real and imaginary parts of W in terms involving... By the way, if you're wondering, I'm 16 and halfway through my bachelor's in pure math. Okay, so... that section is actually surprisingly easy, except for the calculations. That would take forever. If I were any good at Epsilon-Delta, if I were any good at it, this would have taken 10 times less time, okay? It's just those first ones, I wasn't very good at because I never spent any time learning Epsilon-Delta stuff. So, the scene. Okay, so we have that exp of w is equal to z. What can I do about this? Well, I know that exp of w equals the exponential of the real part of w times the exponential of the imaginary part of w. That's just simple stuff, times I, which is going to be equal to I want to set this equal to z. So the exponential, am I deriving it? Or just, it says determine, so I don't know if I need a proof. So z here w will be equal to the absolute value of z plus I times the argument of z. Since exponential w equals exp absolute value z plus I argument z, which is equal to exp of absolute value of z times exp of I arg z. This right here is exp exponential absolute. Oh, it's the natural log of the absolute value of z. Sorry. Since exponential w equals the exponential of the absolute value of natural log absolute value of z times exponential I arg z, which is equal to, right there is the absolute value of z, times, right there is, as you can check, the absolute value z over the absolute value of z, which is just z. So now we're good. 2. Okay, how is the complex logarithm defined? Okay, so log of z is going to be defined to be the natural log absolute value of z plus I times an argument of z, which is sometimes written natural log absolute value of z plus I use z equals I and z equals I minus 1. No, there's a much easier way to do it. I'll tell you it. And then the principal log of z is going to be natural log absolute value of z plus I times the principal argument of z. That's how you I don't know how else I could define it. There's probably something else. And then the simple example is I just use e to the pi I. E to the I pi times e to the I pi is equal to log, is not equal to log of e to the I pi plus log of e to the I pi, because over here, this is just telling me the audio cut. I'm bad when it comes to the audio here. Yeah, got it, guys. So, yeah, and the reason why it's not continuous is for this exact reason. The reason it's not continuous is because log of e to the I times 0 is equal to 0, but log of e to the 2 pi I, or the limit, I should do the limit z approaches 0 of log e to the 2 pi of limit as z approaches 0 of e to the z is equal to 0, but the limit as z approaches 2 pi I of log of e to the z is equal to 2 pi I, even though e to the 0 equals e to the 2 pi I. So that's why. So, what does it mean for a function to be differentiable at a point D? So on a set D, so that means that for every z, that means that the limit as z approaches z0 of f of z minus f of z0 over z minus z0 exists. Cool. That's differentiable. Denote the cut plane by using the fact that log of z is continuous on the cut plane. You do not need to prove this. Prove directly from the definition of differentiability that for all z an element of D, derivative of log z is equal to 1 over z. So let's do this. Limit z goes to z0 of log z minus log z0 over z minus z0. This is limit z approaches z0. Log of z is natural log absolute value of z plus I arg z, and then minus natural log absolute value of z0 minus I arg absolute value of z over z minus z0. How on earth am I going to get anywhere with this? Well, this is going to be the limit z approaches z0 of the natural log of absolute value of z over the absolute value of z0, and then plus I times the arg of z minus arg of z0, which I'm almost certain is just the arg of z minus z0. Like that. This is going to be over z minus z0, and then I'd imagine that I'd split this up, so the limit z approaches z0. You need to skip this. Skip this? Okay, cool. Why not? Next problem. Recall that if b is an element of b to the z is defined as that. Calculate all the values of 1 plus I to the I. That's pretty easy. Let D be a domain and gamma. Okay, that's the definition of the contour integral. Fundamental theorem of contour integration. Stuff about closed contours. Yeah, that's pretty easy. Let G of z equals z over z minus 1. Let C denote the circular contour with center 1 and radius 2. Described and counter. Yeah, that's all pretty simple stuff. Lorentz expansion. Okay, Lorentz expansion. Let's do singularities, I guess. An isolated singularity. What is a... do B7, 2. it was proved in the course that that sum is a power series in Z with the radius convergence R, then f of Z is differentiable on that, okay? And f prime of Z is equal to that. By considering the sum to infinity of an appropriate geometric progression, use this result to prove that 1 over 1 minus z squared equals 1 plus 2z plus 3z squared plus n z to the n minus 1 for absolute value of z less than 1. Okay, so what's an appropriate geometric progression? Okay, so I'm guessing that we just do like something like black pen, red pen would do. Like 1 over 1 minus z is equal to 1 plus z squared plus so on and so forth. So that 1 over 1 minus z squared, that's, okay, so 1 over 1 minus 2, okay. Maybe I just square that. That could work. 1 over 1 minus z squared is going to be equal to 1 plus 2z plus 3z squared. Yeah, so like that. And this is for absolute value of z less than 1. And that's, I'm assuming we could know that fact. So that I could, that, right? That's just simple, like, multiplication there. Subtract z over 1 minus x squared on both sides. Which one are you talking about? Isn't it? Okay, so this is like a course-specific thing. Like, a lot of it is, like, in this course, even though, like, most of it's pretty standard. Okay, state without proofs, Cauchy's residue theorem. So z over 1 minus z squared, subtract that from both sides. Oh! Oh, okay. Yeah, that'll make much more sense. Yeah, sorry. 1 over 1 minus z squared is going to be sum from n equals 1 to infinity a n z to the n. Let's assume that. And then if I subtract what he said to do, 1 minus z squared, subtract z over 1 minus z squared. This is equal to simply 1 over 1 minus z due to the fact that I can combine those. This is equal to the sum from n equals 1 to infinity of a n z to the n minus the sum from n equals 1 to infinity of a n plus 1 times z to the n plus 1, because we just times a n times z to the n plus 1, or moving it down, we could add 1 there. Okay, we need to move it up. Subtract 1 there. Combine those two sums equals the sum from n equals 1 to infinity of a n plus 1 minus a n times z to the n plus 1. I think that's the way to do it. But by the fact that we have this right here, this is equal to the sum from n equals 1 to infinity of z to the n. So let me plus 1 there, plus 1 there, plus 1 there, 0 there, 1 there. Okay, I'm going to need and this is going to be plus just a 1. This is equal to that, so that an plus 1 minus an has to be equal to 1, so that an plus 1 equals 1 plus an, and then we also have it that a1 has to be 1 as well, so that we have it. Bye! So, yeah, I think something along those lines would be how you do it. Okay, so now, let g of z equals 1 over z times 1 minus z squared. Find the Lorentz series for g on the analysis. That one. Okay. That seems easy because we just calculated what the thing was there. So 1 on 1 minus z squared. So the Lorentz thing here is going to be 1 over z plus the sum from n equals 1 to infinity of n, from n equals 2 to infinity of n minus 1 times z to the n. And then that's it. So n equals 1, n times z to the n minus 1. There, that's the Lorentz expansion for that one. Changing variables to w equals z minus 1. Okay, so that would be 1 over z minus 1 plus sum from n equals 1 to infinity of n times z minus 1 to the n minus 1. That's a Lorentz expansion, right? Write down the values of residue of G0 and residue of G1. Residue of G at 0 is 1. And the residue of G at 0 is actually, yeah, it's 1. And the residue of G at 1 is then going to be, get rid of, it's going to be, okay, I have an order. Okay, so, how exactly can I find you're gonna put together a paper on integral manifolds? Cool. Okay, how many viewers do I have? That's the question. 12! That is surprisingly high. I did not expect 12 viewers on this. Just doop. Okay. Residue of G at 1. Okay. So basically what we have to calculate now. Oh, I forgot. There's a thing for residue. Ugh. Let me look at it. Residue. I'm almost certain. Complex. There we are. I want to make sure I'm getting this definition right. Definition: the residue of a meromorphic function f and an isolated singularity a, often denoted residue of fa, or the residue, okay, is a unique value r such that f of z minus r over z minus a has an analytic antiderivative in a punctured disk. Can be calculated using, okay. And one can often find the residue as the coefficient a minus 1 of a Lorentz series. Ah, yeah, okay, so I was right. So, at 1, what exactly is this going to be? I think the residue is going to be 2. Well, the coefficient that it's going up to is infinity. So this isn't like a normal pole. This is a pole like everywhere. No, it isn't. Wait, what am I talking about? So I think the residue is 0. Yeah, I think the residue is 0. Okay, so can I zoom in on the problem again? Yes, of course. Boop. Yep. Okay, so next problem. Suppose f is holomorphic there. It was stated in the course that the coefficient bn of the term is given by that, where CR is a circular contour in D with center Z0. With radius r and elements of 0 to r, described once anti-clockwise. Suppose that m is bigger than 0, such that for all z not equal to 0, we have f of z less than. Use the estimation lemma. Don't know what that is. Can't answer that problem. Let's skip it. Okay. Recall the following formula for the residue. Yep. It's a simple pole. That's how you calculate that. So let f of z equals that. Show that f has simple poles at z equals minus I over 3 minus 3i. Show that residue of f minus I over 3 is 1 over 8i, and calculate residue of f at minus 3i. So, okay, so let's zoom back out, guys. Ba-doop. Cool. Now, okay, so I have f of z equals 1 over 3z squared plus 10iz plus minus 3. That's it. We can factor it. Yo, what's that? It took, okay, Untitled username. Welcome. Welcome. We're doing some complex analysis. This question is asking us to calculate a residue. Okay, so let's calculate the roots here. So they do the roots minus I over 3 and minus 3i, so I'm assuming that the roots here are going to be, it's going to be divided into parts, are you kidding me? 3z plus I and z plus 3i. That would work. 3z squared plus 9z plus iz plus, yeah. So 1 over that, f of z equals. Okay, so okay, how do I show that it has simple poles? Well, right here. Simple z equals minus I over 3 and z equals minus 3i there. Okay, so now residue of f at minus I over 3 is going to be equal to the limit as z approaches minus I over 3 of, and I cancel that part out, so I'm left with 1 over z plus 3I. Plug that in. That's going to be 1 over minus I over 3 plus that. So that's going to be 2/3. 2/3, so 3 minus 3 halves. Minus 3 halves I. Oh, 1 over 8I. Apparently I did something wrong there. 1 over 8I. How on earth is it? Oh, wait, I'm stupid. Because I'd have a, I'd still have a scale out here, which is, no, 6. 6 out here. There's a 6 out there because the 6 goes in right there because of the, yeah, okay. Sorry if that doesn't make sense, but, yeah. Okay. No, wait, it's 2. It's just, no, wait. Yeah, it's just 3. It's just 3. It's just 3. Yeah, sorry. I'm not the best at this. Okay, so residue of f at, what's it going to be? Oh, Felix is back. Welcome back, Felix. Okay, we're going to do minus 3i. Minus 3i is going to be equal to limit z approaches minus 3i. We get rid of that thing, and that time it's actually just going to get completely gotten rid of. 3z plus I minus 3i, that's going to be minus 9i, minus 8i, minus 1 over 8i. That's how you calculate the residues, I guess. Okay, state without proof, Cauchy's residue theorem. Okay. For gamma, a closed contour, and f holomorphic with no poles contained by gamma. Oh, is it residue? It's residue theorem. And f holomorphic with z1 to zn poles. Then the contour integral over gamma of f of z dz is going to be equal to poles contained by gamma. Then we're going to have it that this is going to be equal to the sum from I equals 1 to n of the residue of f with respect to zi. Yes, the stream is going to be over when I'm done. Well, no. I'm going to go ahead and look at a exam for something else and see if that's any harder. And then that's just calculating stuff using the residue theorem. I have a video on that, so you could watch those. So that's the end of the test. So I mean, you guys want me to end it now, or if you want me to do like those examples, but I'm pretty sure I even did that exact example that they tell me to do. I think that's my video on it. So let's go ahead and look at a topology exam. I want to see what a final looks like for topology. Play Minecraft now. Not again. Not this time, buddy boo. Okay, so. Ooh. Okay, so. Let's go to a topology final. here we are. There we are. We have a topology exam now. Let's go ahead and maybe just take a look at it. So define when a topological space X is compact. Prove that a closed subspace. Okay, that's pretty easy. Let that be a function. Define continuity. Extreme value theorem map. Okay. Prove the extreme value theorem. I forgot the extreme value theorem. What is it? Okay, so the bloop. If a real value function f is continuous on the closed interval AB, f must attain a maximum and a minimum? Yeah, that's what I thought it was going to be, but then it did it for X. Oh, generalization to metric and topological spaces. If V and W are topological spaces, F, K is compact. If K is a compact set, and f is a function from k to r, is a continuous function, then f is bounded, and there exists p and q such that f of p equals the supremum of x for... So maybe that's the extreme value theorem it's talking about. Maybe it's talking about it on a closed interval. I'm almost certain it is. Okay, define when a space is connected. That's easy. It just doesn't have a separation into two disjoint open sets. The surjective continuous map between topological spaces. Show that if f is connected, y is connected. That's pretty easy. Okay, provide a counterexample. That is, construct an example of two topological spaces. That's difficult. Define Hausdorff. Prove that compact sets of Hausdorff spaces closed. Provide a counterexample for when the space is not Hausdorff. Define basis. Define the topology generated by a basis. Let X be a set. Define a metric. Let D be a metric. Define the metric topology. Yes. Let X and Y be... Define the product. Okay, X is a topological space. Show that A of X is open if and only if every A and element of A there exists. Okay, that's easy. Okay. Oh, that's a problem question in one of my books. Okay. Okay, we have projections. Okay, this is easy. This is an easy topology exam. So that's just a super easy topology exam. I don't think I need to go over it. So, yeah, let's just do a little mini Ask Me Math, I guess. So, here we are. There. Cool. Ooh, my arm is getting... from holding this mic for so long. Okay. Oh man, I can't even pick up my eraser. Mini Ask Math. Are you doing any putting up problems on your channel soon? Not soon. Probably not even ever. But who cares? ABC uniformly picked from that. What's the probability that ax squared plus bx plus c has at least one real root. Have I heard of Vieta jumping? I've not heard of that. Sounds familiar. So basically, what for that first one, what I'm doing is b squared minus 4ac. What I'm checking is that this has to be bigger than 0. Or bigger than or equal to 0. Because then, if that's the case, it will have one real root. One or more real roots. So what I'm calculating is the probability that b squared is bigger than 4ac. So this is going to be something in 3-dimensional space. So let's do it normally. Let's make this C, let's make this B. So 4AC, I have this little box right here that I'm doing. Like that. So this is the 1x1 box, and then I'm doing 4AC in here. So maybe something like that, and I'm doing all the area below it. So this is like a triple integral. Hey, Raphael, we just got done with the test, so we're doing like a mini Ask Me Math. So this is a triple integral. Let's do, yeah, triple integral is probably the best one to do here. And this is going to be from b equals 0 until b equals 2 rad AC. And then we're going to do AC plane. We're just going, do we have any conditions? No, I don't think so. So let's just do a equals 1 until a equals 0 until a equals 1, and then c equals 0 until c equals 1. I'm almost guaranteed. Yeah, that's it. Okay, it's just that of d b d a d c. Cool. So let's just rewrite this in terms of x, y, and z. So this is from z equals 0 until z equals 2 rad x, y. This is y equals 0, y equals 1, x equals 0, x equals 1, dz, dy, dx. Integral x equals 0 till x equals 1. Integral y equals 0, y equals 1. That right there is going to be 2 square root xy. Let's move the 2 out. Square root xy dy dx. So now doing that in respect to y is, what is that going to be? Okay, that's going to be square root, the antiderivative of that, so that's going to be square root of x times y to the 3/2. And then we also have another term out front, which is 2/3, so this is 4/3. Because that would be 3/2, 1/2, 3/2 times that, it's 2. Yes. Okay, so this is from 0 to 1. Dx equals 4/3 integral from 0 to 1 of, that right there is just going to be 1. So this is just going to be of square root of x dx. Which is also just, I just need to multiply this outside thing. Then I multiply it by 2/3 again until I get 8/9. So the answer is 8/9. Why would we do z equals, no, we're doing the part below it. No, we're doing the part above it. You're right. This is 2 from 1. Okay, so 2 rad xy on the bottom, 1 on the top. Yes, you're right. Sorry. this right here, I did the one part of it, so it's 8 over 9, and then I have to also do the integral x equals 0 to 1, y equals 0 to 1 of 1 dy dx, and I mean, like, it's hard to imagine, but it's 1, so it's actually the exact opposite of that, and it's 1/9. Yeah. What millennium problem do you like most? The Hodge conjecture, that one. So 1/9's the answer. Look at that. I completely demolished that problem right off the bat. Okay, Sergio, let's take a look at your thing. Okay, it's probably 1/9. Cool. It's not 1/9? xy goes from 0 to 1 since the surface z equals 2 intersects the plane z equals 1. Oh, yeah, that's right. So I can't just thank you. Okay. Let me just... You're right, yeah. So we have to take into account the maximal surface, which is this, or xy equals 1/4. This is similar to the other one now. This is like the one we did before. Are you joking me? So I'm going to do y equals 1 over 4x, and we're doing this from y equals... We also have the condition that it's in the box. So we have the condition y equals 1, y equals 0. So that here, would you look at that, it gets split up. Or maybe I just do this part. Yeah, it's just that part, because that's the part that intersects it. So it's going to be from 0 to 1 over 4x. So y equals 0, y equals 1 over 4x, and then x in finality just goes from 1/4 until the end. So x equals 1/4 until x equals 1. Because that part is the actual surface that we're dealing with. I hope I don't have to include that little part. I might be wrong, but... Okay, so let me just get rid of that part because I instantly know it's going to go there. It's 1 minus 2. So let's just do 2 rad xy right now. dy dx. X equals 1 over 4. X equals 1. Okay, right there we're going to have 2 on the outside. Right there we're going to have square root x times y to the 3/2, and I need to have a 4/3 out here. It's from 0 to 1 over 4x. Are you joking me? 0 to 1, 1/4 to 1, unless I'm wrong. And square root of x times... Okay, that's going to be 1, so that's 3/2, that's 1/8, so it's 1 over 6. Okay, so square root of x, I'm just going to calculate it this way, tell me if I'm wrong, and then that's going to be times x to the minus 3/2, which is just 1 over x, so this is x to the minus 1/2. dx 1/6 times Okay, so now I do add 1, 1/3, 1/3. So I get 1/3 there. Oh, then I have to do 1/4. So that's 1/2. So it's a 1/6 again. Okay, so then I have to do the same thing, except I'm going to do just 1 dy dx. It's going to be equal to the, from 1/4 to 1 of right there, I'm going to have 1/4x dx. Right there, I'm going to have 1/4. 1/x dx. That's natural log. So natural log of 1, 0. Natural log of 1/4. So that's 1/4. Multiply that by 2. 1/2. Natural log of 2. Oh, no. Oh, no, I have bad memories of this. So, is it 1/6 minus 1/2 natural log of 2? It's probably not. I might have to add in that little area. 1/6 minus 1/2 natural log of 2. And if it's not that, I'll have to add on to that the area of that tiny little region, which is just 1/4 by a tiny bit. Yeah, so it's going to be something like that. Is it? I don't know. Do I still have viewers? 11 people, yeah. I split it into 2 regions, yeah. So the second region is going to be doing the integral from 0 to 1, integral from 0. So from 0 to 1/4, this one's from 0 to 1. It's 2 square root xy dy dx. What do I get out of that? It's 2 right there. Oh, that's just the thing I did before, which I got an 8 out of 9, except now I have 1/4 there. So that I need to multiply this by 1/4, so it's 2/9. Okay, does this look right? Okay, I'm gonna copy your link. Let me turn on my capture there. Go on to scene 2. Let me go ahead and remove my crop. Filters. Crop pad. Make it invisible. There we are. Okay. Ew. Okay. Let me wow. .com there. Oh, that's what I had. That's what I had. I had the right integral. What are you? Yeah. Okay, cool. So that integral I got right. It looks like 1/6 minus 1/2 natural log of 2. 1/6 minus 1/2 natural log 2. No, I did it wrong. What a surprise. Yep. Would you look at that? What a surprise. Okay, where was my mistake? So that's, yeah, I don't know where I went wrong. 0 to 1/4, 1/4x. X to the minus a half. Maybe that's where I went wrong. Maybe the 1/6 is wrong. Maybe it's a 1/3. So 1/4 there. 1/2, 1/8. 1/8 times that is, yeah. Except, yeah. Yeah, there's no getting around that. Oof. Okay, so that's minus a half, minus 3/2, that's 1/2, yes. Okay. Okay, so x to the minus 1/2 there. Is it a 1/6 or is it a 1/3? Let's do a 1/3 minus it. Still not big enough. 2/3 minus it. 2/3 is too big. 1/2. 1/2 minus it. No. Okay, I guess I was just completely wrong. Okay, well. Oh, hi, Tim. You're back. I'm not doing too good. Okay, let's just move on. Suppose you have a piano, but you can only play a G for 1 second, an A for 2 seconds, a B for 3 seconds, or an F also for 3 seconds. How many 10-second long melodies can you make? That sounds very... Okay, so okay, here's a cool problem, probably. Integrate the integral from 0 to infinity of cosine lambda x over x squared plus a squared dx using Jordan's lemma. Okay, Jordan's lemma. Let's get the statement into here. Okay, so the positive parameter A I don't see how I could use this lemma to evaluate an integral, but I can see how we could use complex analysis to bring this into. So we could say that we can convert this to a contour integral of e to the I lambda x divided by z squared plus a squared. Z squared plus a squared seems like it could be something else. dz. Z squared plus a squared sort of seems like it could be something else. So what's the contour we should do? Well, I'm doing it from z to infinity, so do we have an asymptote somewhere? Doesn't actually look like we have a pole. Not asymptote, pole. So I'm not even sure we need to do like a keyhole contour or anything like that. I think we could just do a circle like this, radius r, and we just make that gamma. And then just increase the r sufficiently. Okay, so maybe I should do a circle and then continue it on to infinity? Let me look at the chat. Yeah, so integrate sine squared of x in under 2 minutes. That's something else. Okay. There could be a way to do this without calculus. Well, not without calculus. Without complex analysis. Do very different things. But are okay, let's do a thing where I make this like a Papa Flammy, I of lambda. So then I prime of lambda is equal to the integral from 0 to infinity of, right there would be minus sine of lambda x times x over x squared plus a squared dx. That's just a normal sine. Yeah, that does not make it any easier to calculate. Let's make it maybe a function of a. Let's do this as an a, I prime of a, integral 0 infinity. Okay, so this is going to be negative cosine lambda x, a on the top, x squared plus a squared on the bottom, and then I square it. That doesn't help. Night, guys. Need some sleep. Quantum mechanics exam today was rough. Thanks for Monica for taking up the exam. I'm not a smart guy, but even I felt that exam was a little disappointing. Yeah. Wait, wait a second. I think this integral is in my complex analysis book. This seems like something flammable maths would do. Flammable maths. Let's see all of his videos. Okay. Are we getting somewhere? Oh, we have cosine of x over x squared plus 1. He has a bunch of videos on that, which is probably what I'm thinking. He got pi over e. So let's use a similar method as him. What does he do? He makes it a function of t, where the top is lambda of it. That's like that. So he does what I did, except he continues with it. Okay, so how on earth do you continue with this? Integral from 0 to infinity minus sine lambda x over x squared plus a squared. Okay, so what he does is he multiplies the top and bottom by x. Then he has x squared plus 1, plus I'm going to have to do a squared minus a squared dx. So this is going to be equal to the minus the integral from 0 to infinity of the sine of lambda x over x, then minus a squared times the integral of minus sine of lambda x over x times x squared plus a squared dx. I think that's what he writes. Except that's minus, so that becomes a plus. And there's not a minus in there. Okay. And then he takes the second derivative. Are you joking me?
If we differentiate in special rule of the likeness, rule for integration, special case, and we can interchange it, turning it into a partial derivative. So the second derivative of this function is just the integral from minus infinity to infinity of del t sine t times x over x squared plus 1 dx. Just like before, differentiating f.
Okay, so then we differentiate it again. So a squared integral from 0 to infinity. 0 to infinity. Sine lambda x cosine. Oh, okay, I see. Cosine lambda x times x over, and then the x cancels out. I get x squared plus a squared again. Oh, would you look at that? And then minus integral from 0 to infinity of cosine of lambda x, of just cosine of lambda x. Okay, I see where we can go from here. And that, unless he excluded it, didn't he? Why did he exclude it? Is it because we knew the value? Oh, yeah, it's negative pi. And also, yeah, so he just assumes that I know it's negative pi. Okay, so let's just get rid of that then. I double prime, got that. We're just back to the same thing. And then you solve a differential equation to get the rest of it. I double prime of lambda over a squared minus I of lambda has to be equal to 0. Okay. Okay, so let's solve the differential equation. I could use Laplace transform. I could definitely use Laplace transform. But I'm not going to do that. There's an easier way, I'm sure. He solves it. I'm just going to do what he did. Yeah, it's just homogeneous. So if I suppose that I of lambda equals some c times e to the at. Okay. Let's make it r. Then this would yield that I double prime of lambda would have to be equal to r squared c times e to the rt. And then, oh, he has lambda. Okay. I'm using lambda instead of t. Right there should be lambda. Right there should be lambda. And here I'm going to have factor out a c. The c doesn't matter in the end. Factor out the e to the r lambda. That doesn't matter in the end. The only thing right here is I have r squared over a squared minus 1 equals 0. So that r equals a. Huh. So I of lambda is equal to a constant times e to the a lambda. Oh, it's plus or minus a. So that plus c1 times that plus c2 times minus a to the lambda. This is going to be at t equals 0. So at lambda equals 0, but I'm evaluating this for general lambda, so now I have this equation that I can't solve. Are you joking me? So I guess this method doesn't work. Yep. Whew, okay. Wait a minute. Wait a minute. I at lambda equals 0 is a boundary condition. He gets I of t equals pi to the e. Oh. Okay, so then after a bunch of steps, he gets I lambda equals pi over e to the lambda. So, yeah, sure. There. Take it. Take it. Yeah, find initial conditions. Do that. That's what you get. Cool. Nice. Would you look at that? Don't use that other lemma, whatever he said. Did I forget a dx? I did. Sorry. Cool. Well, that was a cool, fun time, guys. I did a bunch of stuff. Wasn't that good. Oh, what's your test grade for your class? Okay. Okay. My Lord, my hand is dying. So, maybe let's talk about category theory, because in before Monica fails basic algebra. Shut up. Shut up. I'll fight you. Okay. Whew, okay, so what we've gotten out of this experience is that I cannot do the Epsilon-Delta definition. That's the only thing we learned. Okay. Oh. Boob. Okay, look, I'm gonna redeem myself, and I'm gonna do another thing on this exam, even though it's probably not the best. Okay, so here we have my the original one I had, and I'm gonna look at it again. Yeah, okay, there we go. Do the sine squared problem. Yeah, I could do that. Stupid. Yoop. Okay, integral sine squared of x dx equals the integral sine of x plus 1 over 2d sine of 2x. Sine of 2x plus 1 over 2. That's equal to 1 over 2 times sine of 2x over 2 plus x, and I'm pretty sure it's actually minus. And then plus c QED. Okay. Do the limit laws evaluation question. Yep. That's what I'm going to do. Just to redeem myself from not being good at it. So, I'm going to write down the limit. And, limit x goes to minus 1 of x cubed plus 1 over x cubed minus 4x squared minus 2x plus 3. Okay. They've given me... Yes, we're factoring it. How did you know? Okay. Boop. Okay, we're good. So the thing is, they gave me the root already. It's going to minus 1. Obviously, the root's going to be minus 1. Why else would they make it like that? Okay, so factor out an x plus 1. X plus 1, x cubed minus 4x squared minus 2x plus 3. Okay, it's x squared, x cubed, x squared there. Minus 5x squared minus 2x, that's minus 5. X minus 5x squared. Minus, that's going to be 5x there. And then we get to minus 7 positive 3x. That's going to be plus 3. So 3x plus 3 is 0. Okay, that we can factor not. We cannot factor that. Limit x approaches minus 1 of, this is going to be x plus 1 on the top. X squared minus x plus 1. That might be it. X cubed minus x squared plus x squared plus x minus x and then plus 1. Yeah. So that's going to be over and x plus 1. And then over, and then that right there is x squared minus 5x plus 3. Which then, using the fact that these are going to be equal to 1 on the deleted neighborhood, I can cancel them out and then get x squared minus x plus 1 over x squared minus 5x plus 3. Just plug it in from there. Minus 1 squared minus 1 plus 1 over minus 1 squared minus 5 minus 1 plus 3. Let's evaluate it. It's 1 plus 1 plus 1 over 1 plus 5 plus 3. That's 3 over. That's 9. That's 1 over 3. Wow, look at that. 1 over 3. Okay, cool. Let's do another one. Okay, I did those. Okay, I should probably switch the scene. Okay, I did all of those. So, skip that one. I did all those, except for the Taylor polynomial. I'm just going to quickly do that Taylor polynomial one. Bye-bye, Untitled username. So, let's just quickly do a Taylor series. So we're doing the 6th order Taylor series at 0. So, do you guys remember how to do Taylor series? Yes, of course you do. So, 6th order though. Okay, so f of x is going to be 1 plus x times cosine squared of x. Okay, let's calculate its derivative. Product rule, 1 plus x. Chain rule. So 2, 1 plus x times cosine of x. Multiply that by minus sine of x. And then plus derivative of that, it's just 1 cosine squared of x. Okay, f double prime of x is equal to minus product rule minus 2, 1 plus x. Derivative of cosine of x is sine of x. So that's going to be sine squared of x there. And then plus, except this time it's minus. Minus 2, 1 plus x, cosine squared of x. And then we're going to have plus another one, which is going to be minus 2 cosine of x, sine of x. I see something building up here. And then plus derivative of that, 2 cosine of x, sine of x. Oh, would you look at that? Factor out 1 plus x. Right here, we get sine squared of x minus cosine squared of x. Minus 2 cosine sine. I'm pretty sure that one's sine of 2x. Those cancel each other out. So we're left with this. Okay, what is this? This is 1 plus x. And I'm almost certain that that one right there is cosine of 2x. Because cosine, when I do 2x, I square that. Cosine squared minus sine squared. It's actually minus. Minus out there. And so we got this simple thing. Okay, f triple prime of x is going to be product rule. Okay. Divide by 2, and then, so minus 1/2 1 plus x times sine to x. Oh no, 2. Multiply. 2 on the outside there. Because product rule, derivative of that, yep. Cool. And plus, we're going to have plus, yeah, just minus cosine 2x. Okay, cool. F fourth of x. Okay. Oh, a series made by Taylor polynomials. Taylor polynomial is a polynomial made by taking derivative of multiple. Yeah, I know. Oh, Felix didn't know. Huh. Okay, so the fourth term. So fourth derivative. Minus 2. Okay. Do it again. Woo. Okay. Minus 2, 1. Oh, that goes to positive, actually. Because I did derivative cosine, that's negative. So this right here is cosine of 2x, and because product... Okay, there. Okay, then plus, I'm going to have 2 sine of 2x. And then minus, that becomes a plus 2 sine of 2x. I think I'm doing this right. It just seems like these should cancel out, and then we're left with something much easier. I feel like that should be a negative. Why isn't that one a negative? Because should that be a positive? No, because it's a negative there. And then it wouldn't work. Yeah, okay, so I guess it's right. Okay, let's do fifth one. Fifth. Woo, okay, so 4 times 1 plus x multiplied by another one, 8. And minus 8 sine of 2x plus 4 sine of 2x. So that's going to be 8 cosine of 2x, and I forgot to add on the part where I don't take the derivative, which is going to end up being 4 cosine of 2x. And then I just add on to this, so it's 12 cosine 2x. F6. This is the last one we need, baby. Okay, minus 8. 1 plus x. Okay, we're going to need that to go to a 16 cosine 2x. Plus, part where we don't do it. Okay, so minus 8 sine 2x. And we're adding right there, but it turns into a minus 24 sine 2x. Oh, would you look at that? Those combine. Minus 16, 1 plus x cosine 2x. And minus, that's 232 sine 2x. Absolutely. Plus sine 2x for the third derivative? If I have minus there, that goes out, sine 2x minus, yeah, of a multinomial theorem? I don't know. So let's just plug in zeros into all of these. 1 times cosine 0, 1, that's 1. This one right here. 1, 0, 0, 1, 1. Okay, this one. Oh, wait, I have a simpler formula right here. 1, oh, plug in, yeah, 1, 1, 1. That's 1. This one right here. 1, 0. 1 minus 1. What is this one going to be? 4 plus 0, 4. This one, 0, 12. That's going to be 12. This one, last one, is going to be 16. So I think the answer, if all has gone right, is going to be, drum roll please, 1 plus x over t plus x over 1 plus x squared over 2 plus x cubed over 6 and the third one is minus, so 3 here is minus, and then plus 4 there. Ugh. Okay, so that's going to be x to the 4th over 6 then, because the 4 goes away, and then plus x to the 5th over 12. So the 12, and then we'd have 6 factorial, so 6, so 5 times 5 times 4 times 3. 5 times 4 times 3 is 20, 60, 60. 60 on the bottom, plus x to the 6, 16. 4 times 4. Get rid of 2 of the 4, 6. Okay, so 6. Oh, man. Oh, wait, there's no 6 here. It's 4 and 3. Get rid of the 4 and the 3. So that's 5, 10. 10 on the bottom there. So this one, okay, I could get rid of a 2 there and a 2 there. So 5 times 3 times 3 times, yeah. 5 times 15, 45, 45. Boo. Ka-chow. There we go. There, okay. It's working. Okay, cool. Would you look at that? Oh, that went into the thing where you can't see it. Sorry. Let me just do. Look at that. That's the answer I got. That was quickly done. But yeah, okay, I'm showing it again. Scene 2. Okay, we did all the integral stuff. We did all this stuff, except for calculating the powers of that. Let me do that. So much calculation, yeah, I know. That one really is, that exam's full of just, that's not, I don't like the exam. Okay, it's not a very good one. Okay. Let's calculate the 1 plus I to the power of I. 1 plus I to the power of I, which by definition is the exponential of I times the principal log of 1 plus I. Okay, what is this going to be? It's the exponential. I'm not blaming the exam for the Epsilon-Delta definitions. No, I'm just saying the exam has a lot of calculations. It's not just the Epsilon-Delta definition. Okay, look. I'm bad at proving specific examples with the Epsilon-Delta definition, although I'm good, sort of good with general stuff. I will not deny that I'm bad. Okay, so I times. Okay, they say like all the solutions, all the values. So we're not doing principal log now. So this is going to be natural log. Absolute value of that is just natural log of the square root of 2. And then that's going to be plus I times the argument, and the argument there is pi over 4 plus 2 pi n. That's ends that parentheses, that parenthesis right there. exp of, okay, that becomes negative pi over 4 minus 2 pi n, and then plus I natural log square root 2. Okay, this is going to be exp of this part, pi over 4 minus 2 pi n, multiply this. This is the important part. This is going to be cosine of natural log square root 2 plus I sine square root 2. What do they say the principal log is? E to the minus pi over 4 times that. Yes, I did it right. Would you look at that? Did it right. Cool. Pow. Ka-chow. Okay. let's do contour integration. Why not? Just so it's a learning experience here, guys. Learning experience here. So let's define contour integration. The integral over contour of f of z dz is equal to, so this is for a path AB into C. So right here, this is going to be the integral from A to B of f of gamma of t dt. So it's really simple. And the fundamental theorem of contour integration is that the oh, I forgot what it was. Oh, it's that if f is an antiderivative of f here, then the contour integral of f of z dz is just going to be at the antiderivative there, gamma of b minus f gamma a. I'm pretty sure that's it. And the reason why is because if I do this, by definition, I can just move it here. So integral from a to b, f gamma t dt. Okay, which now all I have to prove is that if I have f, let's look at f of gamma of t. Let's take the derivative of it. Derivative in respect to t of this is going to be equal to, okay, it's going to be f prime gamma of t multiply by gamma prime of t, which that's just f of gamma of t times gamma prime of t, and I'm an idiot. Right here I have to put in a times gamma prime of t dt. So there, right here, the integral here is going to be f of gamma of t gamma prime of t dt. And then from there, this is equal to the integral from a to b of the derivative of f of gamma of t dt, but that derivative canceled out, and then we get f of gamma of a minus f of gamma of b. QED. Nice. Okay. Okay, so what we're doing is we're doing an example of contour integration. So g of z equals z over z minus 1, and the contour we're doing is the circle contour with center 1 and radius 2. So right here and radius 2, circle like that. Not good at drawing circles, but this is the thing where the distance between z and 1 is equal to 2. That's the contour. And a parameterization, of course, is going to be cosine of t plus 1 plus I sine of t, and we need to multiply that by 2. So cosine of t plus 2, 2 cosine of t plus 2, 2I sine of t. Okay, so now let's calculate the thing. Wait! Then straight from this, if this is closed, if this is a closed interval like that, then this is 0, right? Because we're going from f of gamma of A minus f of gamma of B, which is equal to f of gamma of A is going to be what? Gamma of A is going to be... Ooh. So gamma of A is going to be equal to gamma of B, so let's just call it Z minus f of Z, it's going to be 0. So if it's closed contour, then it's 0. So that this tells us that it's 0. Right? It's 0. F of t d of f of z dz g of z. No, wait. Oh, would you look at that? We have a pole. We have a pole, guys. Can't do it. So this is going to be equal to integral from a to b. This is 0 to 2 pi. And this is going to be of this composed. Okay, so that's going to be 2 cosine of t plus 1 plus 2i sine of t. And then the one on the bottom is going to be 2 cosine of t. And then we're just going to have plus 1 and then 2i sine of t dt. Oh my god. Okay. No, we can't use the residue theorem. We can't, no, we're assuming that we don't have a lot of knowledge here. We're assuming that we only know what contour integration is. And then from that, using the theorem, you can get that it's equal to 0 because it's closed. That's just really just simple stuff. But here we have a pole, so we can't just do it. We have a pole there, simple pole, and we can't use the residue theorem. We have to calculate it straight from fundamentals. So I really don't want to multiply the top and bottom by the conjugate, but you have to do that. 2 cosine of t plus 1 and plus 2i sine t, and we're multiplying this by 2 cosine of t plus 1 plus 2 minus 2i sine of t over, and then the sum of the squares there. So that's going to be 4 cosine squared of t plus 4 cosine of t plus 1, and then plus 4 sine squared of t. That just becomes a 4 there, so 4 cosine of t plus 5 on the denominator. And then on the top, oh my god. It says that we're, from the definition of contour integral you gave in 1, calculate the contour. So we have to go straight here. So, okay. 2 cosine there, that's going to be 4 cosine squared t, and then plus 2 cosine of t, and then the 1, we also get a plus 2 cosine of t, so that's 4. And then the 1 to the 1 gives us just a 1. Oh, wait, we're actually going to have a 6 there. Because there's a 2. There's another 2, 4, and then 2 more. And then 2 times, that's going to be plus 2. Okay, and then we also have just 4 sine squared, so that goes to 4, so that goes to 6. So 6 cosine of t plus 6, and then plus the other two values. Oh god. Okay. It's basically the same things. So I'm going to have 4i cosine of t sine of t. And then we're going to, those are going to cancel out, those 4i's. So the only thing we have to worry about here is the 2 there, which will go to the 2 here. So that's going to be minus 4i sine of t, and then 2i, 4i. That's going to be 2i, so minus that. Okay. Over 4 cosine of t plus 5 dt. How are we going to evaluate this? Oh, you can't see anything. Sorry, I keep writing over stuff. Okay. Yeah, I have no clue how we're supposed to evaluate that. I'm dumb. Am I not? Would you look at this? I forgot to multiply by gamma prime. This entire thing's worthless. Because it'll probably be 10 times easier. Okay, multiply by gamma prime. That's going to be minus 2 sine of t plus 2i cosine of t dt. Oh my god. Yeah, how do they expect you to calculate this? How on earth? Using the definition? How am I supposed to calculate this? Yeah, I have no clue. Am I doing the right question? Z over z minus 1. Circular contour. With center 1 and radius 2. There has to be a way where I could use this. But, like, they said to use this definition, so... Oh my god. Okay. Okay, so let's calculate the part at the top. That seems like it could simplify a little bit. That's going to be minus 4 sine of t cosine of t minus 2 sine of 4 sine of t. And then minus 4 sine of another one, that's 8. That doesn't help anything. It only makes it worse. It only makes it so much worse. Everything is just so much worse. So minus 4 sine squared. We have a plus 4 cosine squared. Yeah, no. No, get out of... No, we finished the exam. We skipped over some of the stuff. And this problem seems like nearly impossible without the residue theorem. So there has to be like a way I could simplify the integral beforehand. Okay? Oh, well... Right. because that can't work. So let's do the integral. Rewriting this as z squared plus z over z squared minus 1. Perhaps that is better. What I did there is multiply the top and bottom by z plus 1. The question is that it's over a closed thing. I wish we could use the residue theorem. I just wish so badly. Okay. So let's plug in for gamma. We're doing this from 0 to 2 pi. It's going to be of z squared. No! Why on earth? Yeah, that doesn't seem to help. Okay. Is there a way to simplify this somehow? There has to be a way to simplify this. The last part where we're calculating the contour integral. And you can't do it with the residue theorem. And you have to do it using the parameterization of that circle. Which is like insanely, like, why? They must have learned like a trick around it, right? They had to have learned a trick around it. I'll show it for right there for right now, because it's not blocking anything. So, I think we have to use the parameterization. But if I didn't have to use the parameterization, yeah, I don't think there's a better way to do it. It's just brute force calculation, and it's a really ugly integral. That's all there is to it. Have you tried find vector parameters instead of simple functions than using you can't use Stokes' theorem. No, you have to calculate it using like the principal things. It seems impossible. Can you do change of coordinates? Oh, yeah, maybe we could. But I think we'd have to prove that we could do those change of coordinates. We could do like a translation, and that'd be 10 times easier. Let's do a change of coordinates where w equals z plus 2. So that the contour then would be 2 cosine of t plus 2I sine of t. Really simple. Really simple. Minus 2. So let's do right here. This is going to be w plus 2. No, I need to do minus 2 here, w minus 3 on the bottom, over gamma dw, like that. No, minus 1, sorry. So minus 1, minus 2 on the bottom. That's still, it's the same thing. Yeah, it's the same thing. So let's just try this, okay? Okay, I'm going to need this entire side. Integral from 0 to 2 pi of, and I need to plug in my values. So I'm going to have 2 cosine of t plus 2 plus 2I sine of t. that divided by this same thing, except minus 1. So that's going to be plus 1 there instead of like that. Multiply this by the derivative of this right here, which is going to be minus 2 sine of t plus 2I cosine of t dt. Oh, I did attempt the thing before the stream. I'm just not good at epsilon delta. That's the only thing I was bad at. I could do everything else, except for, like, one example of epsilon delta. Insane. Okay, and this, evidently. Okay. So... thing is, should I calculate this or this first? I think I'm going to calculate the product first instead of the division, because the product might simplify some stuff. So minus 4 cosine of t sine of t. Okay, minus 4 sine of t. And then we need to do that's minus 4 sine of t cosine of t. That feeds into this. And then plus the i's are going to go to 4 cosine squared of t, and then minus 4 cosine squared of t. This is going to be 4 sine squared of t minus 4 cosine squared of t, which I'm pretty sure is just minus 4 minus 4 sine of 2t I, like that. I'm pretty sure I did cosine squared minus sine squared. That's cosine. That's the cosine part. And I need to do cosine squared minus sine squared, but I did sine squared minus cosine squared. So I need to do it like that. Divided by 2 cosine of t plus 1 plus 2I sine of t. And I need to multiply the top and the bottom by the conjugate. Minus 8. Oh my god. Okay, I can factor out a minus 4 actually. So plus 2 there. Nothing there. Oh, 2 cosine of t sine of t. How did I not see this? Okay, equals minus 4. 2 cosine of t sine of t is just sine of 2t. Okay, so this did simplify stuff a bit. So sine of 2t plus 4 sine of t plus 4 cosine of 2t plus sine of t plus I cosine of 2t dt. Okay, what do I do from here? Well, I have a minus 4 outside. Need to multiply this through now. Okay. Okay, so do you know what I think they might have wanted us to do? I think I'm just very dumb. I think I'm just one of the dumbest people alive. Because this could have been simplified immensely if I just would have done 2 to the EIT plus 2 over 2 to the EIT plus 1 times this, which actually turns out to be just a very simple stretch from that which is just I times E. It's just 2 times I times E to the IT. And I was just not smart enough to realize this very simple fact, which I could have just been completely blind to up until this point. Surprisingly, I am considered smart by some people. Now that you know the extent to which I am not smart, let's go ahead and calculate this integral. We multiply the top and the bottom by the conjugate, which is just e to the minus it there. So, now the conjugate of the bottom there is what I'm struggling with. How am I going to calculate this? So let's multiply the... Oh, I can take out a 4i. So 4i there. E to the 2it plus e to... Okay. Right there, I'm going to have e to the it. That's going to be plus 1 over e to the it plus e to the minus it plus 2 dt. Okay. We're getting close to something. Okay, let's make this a plus 2 up here. And then just subtract a 4i times e to the it. 1 over e to the minus it plus 2 dt. Okay, so... that's very close to being something, but still not something. Did the exam have convergence? I want to learn more about pointwise and uniform convergence. It had some stuff about limits, but nothing about convergence. So I guess you just continue on that sort of path with e to the it, and then you're good. Really. Now let me show you some more about the exam. Before this, they had stuff on integrals. Watch my video on Riemann integrals. Let me do the example of integrals, and I think that'll be my last one. How do limits at infinity work with epsilon-delta? It's not epsilon-delta. What it is for any n bigger than 0, there exists... Sorry. For every epsilon bigger than 0, there exists big N bigger than 0, such that if x is bigger than or equal to n, the distance between f of x in whatever the value is going to be less than epsilon. So there's arbitrarily large x such that it's close. They use Cauchy convergence criterion. Okay. This looks like a very complicated example. So here we have the function from 2, 8 into R, defined by f of x equals 1 over 1 over x cubed. And we're going to say that a partition Q sub n is going to be equal to the sum of 2 some eta to the I for 0 less than or equal to I less than or equal to n. And this is for eta to the power of n equals 4, apparently. Show that we're calculating the lower bound of Qn here with f. Okay, this, remember, is the sum from I equals 1 to n of mi times delta xi. Okay, so delta xi here. Okay, do they have a hint? You may assume that the sum from I equals 1 to n of x to the i's, they give me a formula for that sum. Okay, so mi is the supremum of f on that interval. On the interval from between two of these. Now 1 over x cubed is strictly increasing? Decreasing. So it's strictly decreasing, so I just do the last one. Okay. Lowercase m. So I do the first one, which is I minus 1. So this is the sum from I equals 1 to n of, that's going to be 2 eta to the I minus 1. But I have to put in the value here. So it's 1 over 8 eta to the I minus 1. Multiply this by eta to the I minus eta to the I minus 1. What do I get from this? Sum from I equals 1 to n. Okay. It's 1 over 8. This is going to be the sum of eta over 8. Yep, and then plus the sum from I equals 1 to n. Sorry, minus the sum of 1 over 8. That can't be right. I forgot to multiply this by 3, so that's 3i minus 3. That's the reason why. I knew it couldn't have been that simple. So this is going to be the sum of, so the eta is going to be on the bottom for both of these. Let's take out a 1/8. Okay, then we're going to have 1 over eta to the 2i minus 3 minus 1/8 sum from I equals 1 to n of 1 over eta to the 2i minus 2. What formula are they giving me? That's not going to help at all. Oops, wait. It's 2. So I need 2 there. So that becomes a 4. So that's a 1/4 here, 1/4 here. Okay, how? I'm doing the question, an example of calculating a Riemann integral. Let me show you. Right there. Right there. Okay. So, 1 over 4. Huh. Okay, so these sums, okay, so yeah, so these sums are weird, so let's just go over them. This is going to be 1 over eta to the minus 1, so it's going to be eta plus, do they have it in terms of n at all for the final result? No, it's in terms of eta. So this is eta. So really, this is like adding up the odd numbers. So 1 over, at 2, it's going to be 1 over eta, and then 1 over eta squared plus 1 over, no, eta cubed, 1 over eta to the 5th, so on, so forth. Then minus a quarter times is 1, and then plus 1 over eta squared plus 1 over eta to the 4th. Oh, I see. I see what the formula is. I see what they're doing. So right here I get 1 over 4 eta minus 1 plus 1 over eta minus 1 over eta squared plus 1 over eta cubed minus 1 over eta to the 4th plus so on and so forth. Okay, so I don't necessarily see how the formula they gave us is correct. So this is an alternating sum of the powers. So this is the alternating sums. 1 quarter the sum from I equals 1 to n. So it's actually going to be from I equals negative 1 until n of eta to the I of negative 1 to the I plus 1 over eta to the I. You have 1 minus eta to the minus 1 times the sum of that. Okay, so I don't see how their formula helps. Oh wait, I see how it helps. I'm very dumb. Okay, so this right here is basically going to be negative eta, negative 1 over eta to the I, negative 1 over eta to the I. Very close to doing that. Except I have to put a negative out here so that I have the correct sign. So this is minus 1 over 4 times, and then I can use the formula. So that's going to be 1 over eta, or minus 1 over eta, times 1 plus 1 over eta to the n, or it's actually going to be minus 1 to the n, and then over 1 plus 1 over eta. Which, I see the answer, yeah, it gives us the answer. So then, from there, I'm just going to derive it. I can make that a quarter. It's going to be 1 over eta minus 1 over eta to the... Oh, right there is a quarter. Because eta to the n is 4. That was our condition. So that's a quarter, that's 3/4. That 1 over eta goes to the bottom, I'm assuming. So I got 3, that's going to be 16 on the bottom. Oh, where's the 5? I need to multiply this by 5. Actually, I need to multiply it by 5/4. Where on earth did that go? That's okay. That's okay. That's times eta, and then times. Oh, right there I have a 1 plus 1 over eta. Multiply the top and the bottom by eta to get eta plus 1. 3 eta on the top. Nope, didn't get it. You got 1/4. Okay, so I'm close. I got close. So you get the idea. Prove that f is integrable over 2, 8 and find the value of the integral. So it's integrable. Basically, all I have to do is prove that the supremums and infimums work out. Okay, so yeah. So that's how you do that. Cool. I have to go to bed soon, because I like to have a consistent sleep schedule. So, now to prove that f is integrable, just prove that the things align, that the limits here align. So, my hand is like dead. Oh my god. Oh. Oh my god. Ah. Okay. Still have 6 people watching. Insane. Okay. So, let's... Okay, guys. That was an interesting experience. Hope you all have a good time.